Hello there, welcome back to STR8CHEM. In this video, we're going to learn about the Chatelier principle, and this principle states that if a stress is applied to a reaction that is already at equilibrium, the reaction will counteract the way to reduce the effects of the stress or to relieve the stress to gain a new set of equilibrium. There are three types of stress that you need to know for the Chatelier principle. The first one we're going to look at is on concentration, which is the easiest one. And then we're going to look at the effects of temperature. And then the third one, we're going to look at pressure. And usually when we talk about pressure, it will come together with volume. So these are the three stress that we look at on the discussion about the Chatelier principle. Now we're going to look at the effects of changing temperature on a system at equilibrium. The value of equilibrium constant K is significantly affected by the change in temperature of the system. So this is quite unique only for temperature, because when you change concentration, when you change pressure and volume, the K value of a system that is at equilibrium will not going to change. Okay, so in fact, the system will try to achieve the set equilibrium constant. But in the case of temperature, when we change the temperature, you will have a shifting and they will achieve a new set of equilibrium, and in the same time, the value of K will also going to change. To understand the effect of temperature, we have to consider two situations. So we need to know what does it mean by exothermic, and the other one, endothermic. These are the two type of situation that we can have for the effects of temperature. We have to consider whether your forward reaction will be exothermic or whether your forward reaction will be endothermic. Exothermic simply means you are releasing heat, so it means when you have the reaction happening, the forward reaction will release heat. Endothermic, in the other hand, is more towards absorbing heat if you want to produce the product for the forward reaction. So essentially, exothermic is just the opposites of endothermic and vice versa. Let's consider this reaction over here. Most of the time, you're going to have a balanced equation given to you with the phases on every species to tell you that whether it is going to be homogeneous or heterogeneous. So what we have here, all of them are in gaseous phase. So we know that these are homogeneous reaction. But in cases like if you want to know the effects of changing temperature, the question in exam, they're going to give you information about the delta H. Delta H over here, this is what we call as the enthalpy. Okay, so this is your enthalpy. And when you look at the value of the enthalpy right now for this particular reaction, we have a negative value right here. We have a negative value. So when you see a negative value, no matter what the magnitude will be, but if you see a negative, automatically you'll know that this is going to be exothermic. Okay, so you have an exothermic reaction over here. So for exothermic reaction, like what we have said just now, for exothermic reaction, heat is released for the forward reaction. This is a very important concept that you need to know about exothermic reaction. We do know that now when you have negative sign for the enthalpy, that one will be exothermic, so heat will be released at the forward reaction. Don't forget, forward reaction is this, going to your right hand side, and the reverse reaction would be going to the opposite direction, which is this one, to your left hand side. Okay, so again, forward and reverse. So when you look at this data over here given to you, the value of enthalpy, always imagine forward reaction. That will be considered the most. Okay, so we can consider that the heat will be part of the product for exothermic. So just now we have considered that this whole thing over here is exothermic. And how do we know that? From the value of enthalpy given to you in exams or in the question. So when the reaction is exothermic, heat will be released for the forward reaction as part of the product. So when you apply the same kind of thinking for concentration, you can fairly guess that if you increase the temperature here, the reaction will shift to the left because you are increasing heat that is on the product side. So when you reduce the heat, what happened? The equilibrium will shift to the right. Okay, so you can make that kind of guess at this point. Okay, so when you look at here, if we increase the temperature of the system, you need to remember when we increase the temperature, you are going to be affecting all of these species at the same time. Unlike concentration, when we change the concentration of, let's say, NH3, you are only changing the concentration of NH3, but you're not changing the concentration of here. However, the concentrations will correspond to the changing of concentration that you have done on NH3. But when we change the temperature, when we manipulate the temperature, you cannot just manipulating temperature for one species, but when you change the temperature of the system, you are changing for all of them at the same time. That's why we use the word the system over here. Because when you change the temperature of the reaction, all of them will be experiencing the same type of manipulation. Okay, so what happened when we increase the temperature of the system? So basically what happened here, like what we have predicted, the equilibrium first will shift to the left. Okay, the equilibrium will shift to the left. Because when you increase the temperature, what happened to the heat right over here? The heat will increase. So when the heat will increase, to counteract to that change, you will tend to move towards somewhere that will less heated, which is, in this case, for exothermic, would be your reactant side. So you increase the heat and the equilibrium will shift to the left. So you can say that you can, like I said, you can think in a way that you are changing the concentration in the effective concentration. So when you change the temperature to be even higher, the equilibrium will shift to the left. So what happened? The reason is that you want to absorb the added heat. You add the heat by increasing the temperature, so the system will counteract to absorb the heat. So who will be absorbing the heat? The reactants will be the one that will absorb the heat. As you can see, your product over here, it does not want to absorb the heat. In fact, it will be existing together with the heat. The heat will be part of the product as well. But for the reactants, they will absorb the heat. So when you add heat into your system, you will need to produce more of your reactants in order for you to absorb the added heat. Therefore, more reactants will be produced, less product will be produced, and now the K value will decrease. Okay, the K value of the system will decrease. Why does the K value decrease? Because if I'm gonna write here, if you look at this chemical equilibrium, the K expression would be, if we take in terms of concentration, it's like this. Okay, so when you increase the temperature just now, what happened? You're going to be providing more heat to the system over here. So the heat will increase, and that will not going to be in equilibrium. So to counteract that change, stress, you will need to produce more reactants to absorb the added heat. So when more reactants are produced, you will have bigger number down here, making the value of Kc to be smaller, to be decreasing, because the value that you have here will be bigger and bigger, and the value you have on top here will be getting smaller and smaller as you increase the temperature. So that's why the K value will decrease. So it's very important for you to know how to understand how to interpret your equilibrium constant expression. So when you decrease the temperature of the system, you can guess what's going to happen now. When you decrease the temperature of the whole system over here, what happened? You will start to lose the heat. So when you start to lose the heat, the equilibrium is not obtained now. In order for the system to counteract with that change in temperature, you will need to produce more of your products, and you will be releasing more heat. Why do you want to release more heat? Because you have decreased the temperature of the system. Therefore, the system wants to achieve a new set of equilibrium. So you will need to produce more product over here and also heat. And yes, equilibrium will shift to the right when you decrease the temperature, because right now when you decrease the temperature, you are losing heat. So we want to make more heat. Therefore, for you to do that, for the reaction to do that, the reaction will proceed to the right and to make more heat. To release more heat, less reactants will be formed or produced, and more products will be produced. And the K value of the system will increase. If we go back to the K expression here, if you have more of your product now and less of your reactants, of course, your K value will be bigger in the case of decreasing temperature. So that is the case of exothermic. Now let's have a look at one example for endothermic reaction. Yes, like what we have discussed just now, exothermic, endothermic are the opposite of one another. So if exothermic will be negative, the value of enthalpy for endothermic will be positive. So when you look at your reaction here, when you have the delta H value to be positive, this is what we call as, okay, this is endothermic reaction. So in the endothermic reaction, heat is absorbed by the reactants to make products, in brackets, forward reaction. So it's still going to be the same concept in terms of forward reverse. So we're going to look at the forward reaction the most when we're considering the effects of temperature on the system at equilibrium. When I see delta H over here, when I know the value is positive, like this case, I do know that the forward reaction will be endothermic. Therefore, my reactants needs to absorb heat in order for the forward reaction to proceed to make your product. So let's have a look at this. So if we consider that the heat now will be part of the reactants, the opposite to what we have at the exothermic just now. So when you increase the heats, the reaction will proceed to your right. And when you reduce the heats or you decrease the heats, the system, the reaction will proceed to the left. So it's quite easy. It's the same concept that we have used for exothermic just now. The only difference over here, heats for endothermic will be part of your reactants. So when you increase the heats, the equilibrium shifts to the right. When you increase, so you will shift to the right because now you will be able to make more of your products. Why do you need to make more of your products? Because in the reaction over here, NO2 is the one that will be able to absorb heat, and 2O4 will not going to be able to absorb as much heat as NO2 can. Okay, so to absorb the added heat, you want to move to the right. When you increase the temperature of the system, you will have excess heat, you will have added heat, and that added heat will need to be absorbed by your product. And for you to do that, for the reaction to do that, you will need to shift to the right. You're going to make less of this and you're going to make more of your NO2. Okay? Thus, the K value will increase. So it's the same as what we have looked at the equilibrium constant expression just now. So when you have bigger product, when the product is become more and more and your reactant will be less and less, you will have K value bigger because the K expression is in terms of product over reactant. So it will be the opposites for when you decrease the temperature for endothermic. So when you decrease the temperature of the system, you will start to lose heat. And when you start to lose heat, what will happen? We need to make more of this heat in order for the equilibrium to be retained or obtained. So equilibrium will shift to the left. You will need to release more heat to the system because now the temperature of the system has dropped. So we need to make more of that heat for you to get that equilibrium. Less product will be produced, more reactants will be made, okay, because we do not want to make more of this at lower temperature. At lower temperature, this one will keep absorbing the heat, so we don't want this to be more in the system at much lower temperature, so we're going to shift to the left. So what happens to the K value? The K value will decrease. Now, before we're going to end for the temperature, changing of temperature for Le Chatelier's principle, you need to remember that only by changing temperature, the K value of the equilibrium system will change. Only by changing the temperature, K will change. That's why when you read question problems in exams, they're always going to mention at what temperature for a certain reaction at equilibrium, because at different temperature, you will have different value of K. However, for changing concentration and changing pressure and volume, K value of the reaction will remain constant. It will always going to be the same. So you will just need to try to get the value of Q equals to K when you are changing the concentration, pressure, and volume. But by changing the temperature, you are changing the value of K as well.